We're going to start now talking about polar form of complex numbers. Up to now, we've only talked about rectangular form. So we're going to look at a second way to represent the same complex numbers. So as you see here, if we have a vector representing a complex number, which in this case would be a plus bi, or bj, then we can also represent it using the polar form, which is r cos theta plus r sine theta times j. Or if you factor out the r, you get this form here. And where these pieces come from is basically trigonometry. If this is a vector of a plus bi, then we know that the distance on the real axis here is a, and we know that the distance in the imaginary axis is b. In that case, we know that r squared equals a squared plus b squared from Pythagorean theorem, because this would be a perpendicular. And we know that the tan of theta is opposite over adjacent, or the inverse tan of theta, or the inverse tan of opposite over adjacent is theta. So we can calculate theta that way. And theta is our angle here, and r is the absolute value or modulus, or it's the distance from the origin to the end of the vector. So what we have in polar form is a different way to represent a vector. So the vector is uniquely defined by either a plus bi or a plus bj, or the length of the vector and the angle. If we look at an example now, if we want to represent this complex number, we have 3 on the real axis, 4 in the imaginary, so here's our vector. And we want to change this now so we can represent it in polar form. Well, we can drop this perpendicular. We know this over here is a height of 4. We know this down here is 3, in which case we can calculate r is equal to the square root of 4 squared plus 3 squared. And if you do that, you find the answer is 5. So r is 5. Theta comes from the tan inverse. So theta is the tan inverse of 4 over 3. Opposite, here's theta, opposite over adjacent. And that's always going to be b over a. And in this case, that's 53.1 degrees. So 3 plus 4j is equivalent to, in polar form, r angle theta 53.1 degrees. And written in longer hand, this is the short way to write it. That would be equivalent to, down in this box, r angle theta. Or we can say, using this form, 5 cosine of 53.1 plus j sine of 53.1. So that would be the equivalent to 3 plus 4j. Those are the same vector. A couple of things to remember: r is always positive because we're always going to be talking about a distance. It won't matter what quadrant we're in. If we can't get the exact value of the angle, we should round it to 1 decimal place. And we should always express the angles as positive values. So if we do find ourselves with negative angles, we have to do the correct addition to get it to the equivalent or coterminal positive angle. Moving on then, we can represent any rectangular complex number in polar form. And here we have interesting examples because we have just 5, -5, 7j, and -7j. So these are actually our quadrantal angles, or the angles that end on our axes. So 5, the vector is simply 5 units over here. So the distance from the origin to 5 is 5. So in this case, r equals 5. Theta is the angle from the x-axis to the vector. And in this case, they're the same. So the angle is 0. In which case, in polar form, we get 5 and 0. Similarly here, -5 means we're over here 5 units. So here's our vector. If we're 5 units here, doesn't matter if it's negative or positive, r is always positive, so the distance is 5. The angle this time, from here all the way over, is 180. And so we see that this is simply 5 and 180 degrees. Using the same idea, we can do 7i, and maybe we'll sketch it again. 7j would be up here, and so hopefully you can see we get 7 and the angle is 90. And here we're coming down bottom. There's our vector. So again, distance is 7, and now we need 270 degrees. So these are the equivalent forms of these rectangular complex numbers. These are polar complex numbers. The next example here, we're asked to convert from the given polar form to rectangular form. If we go ahead and do that up here, all we need to do is write it in the expanded form. So that's 3 cosine 45 plus 3 sine of 45. And that's just, or 3 sine j of 45. That's just using what polar form means. This is in polar form. That's the long version of this. Now you just put this on your calculator. 3 times the cosine of 45 and 3 times the sine of 45, leaving of course the j because that's part of our rectangular form, and we get the answer of 2.12 plus 2.12j. Now it's in rectangular form. And we can do the same for each of these. So b will stick over here. We would write it as 2 cosine. Now we don't want radians, we want degrees. So you'd have to convert that to degrees first, and that's 60 degrees. Plus 2i or j sine 60. Again, straight on the calculator, 2 cosine of 60 is 2, plus 2 times sine 60 is 1.73, and we leave the j. And finally for c, we do the same thing, 7 cosine, and we can actually leave negative 70, or we can change it to its positive equivalent. If you're not sure how to change it to the positive, well, negative 70 would be, if we look at our diagram up here, right here in quadrant 4. So negative 70, we'd have to add 360, and we'd find out that's the same as 290 degrees positive. So both of these are the same. So if we change to the longhand form and stick it on our calculator, we should get the answer 6.95 minus 6.58j. And that's the rectangular form equivalent. We'll stop there for this video. In the next video, we'll pick up with the graphs below and changing those to both rectangular and polar form.